So here's our electron transport chain activity that we were doing last class, and a couple people asked if I would film this demo, so here we go. So we have all of the pieces of our electron transport chain labeled. So we have the proteins, complex 1, 2, 3, and 4. You'll notice complex 2 does not go all the way through the membrane. And we have our molecule of Q, and Q can grab electrons from complex 1 as well as electrons from complex 2, and it's lipophilic, so it can diffuse through this plasma membrane and eventually deliver electrons to complex 3. And then cytochrome C is associated, this is a soluble protein found in the intermembrane space, and it'll take electrons from complex 3 and deliver them to complex 4. And as I pointed out in class, these proteins and molecules are arranged from those with the lowest redox potential, meaning they associate with electrons less than those with the highest redox potential, oxygen being at the bottom. And these atoms form really tight bonds with electrons. So they have the highest redox potential and the lowest potential energy, where you have high potential energy up here, okay? And we're going to use this shift in from high potential energy to low potential energy, like going down a waterfall, to generate a electrochemical gradient. So let's talk about how that happens. So the first step I'm going to focus on is the delivery of an electron from NADH. Okay, so NADH is going to donate an electron to complex 1. So it's going to donate an electron to complex 1, and this is going to mean that NADH is going to be converted into NAD+. That electron from complex 1 is then donated to Q, and then Q carries that to complex 3. And when that electron is donated from complex 1 to Q, 4 protons are pumped through into the intermembrane space. So here we have 4 protons in that intermembrane space. And then Q is going to unload its electron and diffuse back. And then complex 3 is going to donate its electron, that same electron, to cytochrome C. And when that happens, 4 more protons are pumped into the intermembrane space. Okay, so now we have 8 protons in this space. And then cytochrome C is then going to take that electron and donate it to complex 4. And then this is going to happen twice. Okay, so let's follow this again. We have an electron here being donated from NADH and being taken by Q to complex 3. We'll get another 4 electrons, 1, 2, 3, 4. And then Q is going to go back. Cytochrome C at this point is going to diffuse back, and it's going to take this electron from 3 to 4. We're going to get another 4 electrons, or 4 protons. 1, 2, that one's upside down, 3, 4. And then what happens is there's now going to be 2 electrons. This electron got flipped over. So now we have 2 electrons. These are going to be donated to half of a water molecule to form water. So oxygen is going to be consumed in this process, and our product is going to be water. And when this happens, 2 more electrons are pumped into this space. So 2 more electrons, 2 more protons, and another 2 protons for each electron. So you can see now we've generated quite an electrochemical gradient in this space, right? And this has been done by passing electrons from molecules with low redox potential to high redox potential. So we've converted chemical energy into electrical energy. So if you were able to stick a probe and measure voltage in this space, you'd see relatively high voltage, right, because of this chemical energy. Okay, so that's that process. One thing I want to point out is that FADH donates its electron to complex 2, okay? So as I mentioned before, Q can also pick up electrons, but it's going to go straight to complex 3. And so this is the reason why the donation of electrons from FADH2 to produce FAD, it doesn't result in as much of the proton gradient because it joins the electron transport chain after complex 1. So it's losing those first 4 protons that are pumped through into the intermembrane space. Okay, so let's talk about what we're going to do with this proton gradient. Okay, so that moves us over to the next part of our electron transport chain. So now we're going to use this proton motive force to follow the flow of protons down their concentration gradient. We're going to convert that into energy. The process by which we're going to make ATP now is known as oxidative phosphorylation, because we relied on the whole process of the oxidation of carbon to get to the production of ATP here. So every time 4 protons flow down its concentration gradient through the ATP synthase, so 1, 2, 3, 4, this chemical energy is going to be converted into mechanical energy. So that part of the ATPase is essentially a rotor, and it's going to be spinning, and it's going to be spinning at 1,500 miles per hour. That mechanical energy is then going to be very quickly converted back into chemical energy. So this is going to cause the ATPase to basically stick inorganic phosphate onto ADP to make ATP. And so that's how ATP is made. So just to point out, right, we have chemical energy into electrical energy, into mechanical energy, and then back into a usable form of chemical energy. So that's the overall process of oxidative phosphorylation to generate ATP. So the numbers I used, these are theoretical numbers that could be achieved in a isolated mitochondria or perhaps in a test tube, but very rarely happen biologically, because usually in this membrane space are proton pumps or proton channels. And so when protons go now against their concentration gradient, instead of creating chemical energy, they can create heat. And this is used by animals in hibernation. So again, these are just hypothetical numbers, but I think using them does a really nice job illustrating all the places in which energy changes form in the electron transport chain. So hopefully that video, you can watch it and then definitely try it on your own. Only when you try it on your own will it really be like, I get it now. Okay, so I'll see you all in class. Thanks, bye.